Hi and welcome back. So, are you ready to continue with creating our shingles? I hope so, because now what we're going to do is, remember in my Photoshop illustration, which I showed you in the last video, I was talking about randomly offsetting, and when we had our UV space, we were offsetting the piece itself. However, now we can also offset the whole canvas. We can have our original piece stay in place and our canvas is going to move, which would be more beneficial because then we have to move it back same place where it was and the same rotation, and it would be much easier if it would stay in the origin of the grid. So that is why we're going to offset the whole canvas rather than offsetting our original piece. And you may argue that here we only have to offset 4 points and here we're going to offset more, but that is a trade-off. So attribute wrangle, let's grab that. So we would need our canvas, obviously. And we would need to know the dimensions of our original piece. That is why I'm going to connect match size. And I'm going to call this random offset. And it has absolutely the same principle as we used when we were dealing with our UVs. So first things first, you would need a seed, because it's going to, well, the name speaks for itself, random offset. And so first things we need to get the dimensions. Get the dimensions of the roof piece. So vector bounding box maximum and bounding box minimum. We would need those because we're going to use get bounding box expression. So first index input, and we will input the variables we just created. So bounding box maximum and bounding box minimum. And now we can calculate the height, which is bounding box maximum.y minus bounding box minimum.y. And I'm just going to copy this line. Not 2 lines, 1 line, please. And I'm going to just rename this to width. And here I just want to replace y's with x's. Yes. So now we want to calculate free space of the canvas. And we know the dimensions of the canvas are 10 by 10. That is why I'm not going to create variables for those. I'm just going to hard code it. So free height is 10 minus height. And free width is a 10 minus width. And now we can create random offset. So float offset height is random of our seed. And then we just want to fit it between its original values of 0 and 1 and 0 and free height. And we want to do the same thing, but with the width. So random offset plus some random number, and we want to offset it between its original values and free width. And now we can create the vector. So now we say offset the canvas. So vector offset is a set of our offset width, offset height, and nothing in Z because we don't want to move it in Z. And now we just simply add it to our current position of the point. And we're going to do it for all the points. So apply. And we have these types. Offset width. Oh. So apply. Yes. And as you can see, we moved it quite a bit. So let's see what's happening. Is it just the update? So yeah, I found a mistake in get bounding box. First you input bounding box minimum and then bounding box maximum. I did it the other way around, so sorry for that. So apply and accept. Oh yeah, that's my checks when I was looking for an error. So yeah, as you can see now, we always have the original piece inside of our canvas. So that is great. So the next thing we want to do is we want to cut out this piece out of that. And the way we're going to do it is we're going to use those edges as the direction of the blades, so to say, if you imagine that it is a factory and the blades are the click node. So for that, we would need to sort our original piece by vertex order. And now we're going to grab a wrangle node and we're going to create the vectors that would represent our edges. So I would call it edge normals. And yeah, for every point, we would grab a neighbor for every point, which is a point number plus 1. And all of that is a modular of n points in the 0 index input. We want to grab the position of our neighbor, so neighbor position is point 0p and neighbor. So let's comment it out right away. Get neighbor position, and our normal neighbor position minus the current position. Apply and set, and as you can see, our normals, and I'm gonna multiply it so you can see. So I will just say multiply it by 3. Yeah. So that is our blades. So let's use them. Let's create a for each subnet, which we will call clip. Let's color it. Let's connect our randomly offset grid as well. And in here, we would do it for each number, and we're always going to do it 4 times. So you can safely input that. Or well, let's actually connect it to our point number. So let's dive into it. And in here, and one thing I forgot to do is we want to uncheck merge results. And we actually want to switch these ones around, because we're going to cut the canvas, and this is just going to be the driver. So here, let's create a null. We will call it in cut points, and we want to locate. So in here, we want to clip and clip. That's going to be our name. So let's copy that, come back, and our blast, we're going to create a stamp. And delete and select it. And we want the points, not the primitive point. So yeah, that is our cut. So let's grab a clip node. We have our canvas. So in the clip node, we're going to say that, first of all, for now, we will keep all the primitives. The origin is a centroid of our blast. Let's actually, we should rename that. So, oops. Dx and dy. We do not care for z because we're not moving anything in z axis. We're only working with kind of 2 dimensions. And I'm going to rename that to locate. So that is our point. Well, it updated to another point, but that is our cut, just where we expect it. However, the question becomes, do we keep primitive above the plane or below the plane? And in this case, well, it makes sense to keep it above the plane, so let's go up. And I do not know why it wants to. For some reason it wants to regenerate it 1,000,000 times, so wait a second, I'm just going to test it with just a grid. So XY plane. So yeah, we randomly offset, we clip it. Why do we clip it only once? Oh, because we had number range going from, yeah. So sorry for that, we have to fix it to this number. You have to go from the first index input because that's where our edges are. And yeah. So the direction is, in X we want to input Y. So we want to go to the locate, and we want to grab the first point. We're going to grab its normal and Y. And we're going to do same for Y but with X. And now if we go up, as you can see, we have the outline of our roof piece. So the question becomes, do we keep primitive above the plane or primitive below? And in this case, even neither work. I actually wanted to show you one thing, but I didn't expect it not to have anything if we do that. And the thing was that when we have these cuts, I actually do not want to keep the last point. And the reason for that is I do not want the last cut to be so abrupt. And I actually didn't expect that we wouldn't keep anything. in our clip. So for now, I'll keep all primitives. But as you can see, this is the last cut. It would be very sharp if we keep it like this way we have set up here. So let me remove this line. So the way we're going to delete the last point is, well, it is not actually the last. I'm telling it's last. I'm lying to you right here. It's not the last. It's the one that goes on the bottom. And the way we're going to track it is we're going to say that, first of all, we want to know its relative position. So relative position, relative bounding box. And we want to say that if it's a relative position that y smaller than 0.5 and its absolute n of its normal in x is bigger than absolute of its normal in y, because, well, it doesn't go in y, it goes only in x, then we do not want this point. Remove point 0 num. So apply and accept, and as you can see, we got rid of this last point. And to check everything, we have it for every single piece. Every single piece lost its last point. So now, when we have our clip, so yeah, that happens if we go above, and that is what happens if we have below. For some reason, it doesn't keep the below one, which really, really surprises me. That is very surprising. So let me get another clip, and we're going to do a switch node. We're going to set this one above the plane, and we're going to go up, and we're going to switch. We're going to say if there is no points in clip, so there is nothing left, we want to clip 1. So let's go up. And yeah, for some reason it doesn't keep the ones I intended to keep. Yeah, I know what it was. I forgot one tiny small thing. We have to make a direction of minus in y. Let me reconnect that. Let's go up. And here as well, minus. Let's go up. So now, so this is above the plane, this is below the plane. Doesn't update or something? Oh yeah. And now, what I wanted to show you from the very first part is we get rid of this condition that we had. We have all of our pieces. And if I connect the canvas instead of the grid, as you can see, our cut is very abrupt in the end. And all of our pieces have that. All of our pieces end very abruptly. And that is why I made this check. And I asked it not to do the last cut, because the way I'm going to do that cut, and yeah, the switch we actually needed, so I'm not going to get rid of that. Because the way I'm going to do it with a group. So let me grab a group. And the way we're going to do it is we're going to enable a bounding box, yes. And, well, size in X, we already have the correct cut. But the question becomes of Y. And the way we're going to do Y is we're going to say that bounding box of, let's see what we have. Edge normals. Yeah, edge normals is a good one. Edge normals. dy maximum, and we're going to subtract dy minimum. Apply and accept. So that is what we have. And we're going to include entities that are not wholly contained. So now, if I use the plus node, and I asked it to keep only group 1, now, as you can see, our end is not so abrupt because some shingles are not deleted. And they would have if we skipped this constraint. So as you can see, very big difference. So let's call this one keep, and locate keep, and here's also keep. So yeah, that is pretty much it. So now all we have to do is put our roof back. So the way we're going to do it is we're going to grab a wrangle node again. So we call it rotate back, And we will have to get many things because we want to have all these rotations plugged in here, which might look very noisy when I think about it. So yeah, let's do it slightly different. So one thing we would need anyway is from each you would need to get a centroid. So let's do that because we're going to rotate and let's say transform back. Yeah, because we're going to rotate and translate. So transform back, and here we will get centroid, input center pivots, uniform scale. Yes, that's good enough. We will connect it in here. And then here, edit parameter interface, you would need to grab two angles. So we would say angle Y, which we created with our wrangle nodes. And here we want to angle XZ, angle XZ. So apply and accept. And we're going to grab them from this rotation. So angle XZ is a detail of rotation XZ, and we just want to know the angle. And the same here, detail, and I want to know rotation in Y, angle, and 0. So here are our angles. And let's start writing. So we have all the information we need, and let's color it. The way we're going to start is we will create a matrix where we'll get all of our transformations. So transform, and currently it wouldn't do anything, so we just identified, didn't. So let's grab our rotation in X and Z, which is a channel angle XZ, as well as our rotation in Y, which is a channel angle Y. And we will also need to know the normal of our original position. So vector normal, and we're going to grab it from our first index input, normal, and 0. So we want to check, first of all, if we have any rotation in Z. So normal.z, we're going to rint it, to check whether it is not 0. And if it is not 0, we want to rotate in X. So I'm going to create actually a vector, which I'm going to call rotation XZ, and I'm going to call it vector. As well as I will create a rotation Y vector right away. And in here, we do not have any doubts. It is a Y vector. And in here, we want to say that if we have something in Z, we want to rotate in X. So rotate XZ vector is an X1. In other case, we want to rotate in Z axis. So I will copy this and yeah, make it X. Perfect. So now what I want to do is I want to rotate our matrix, so transform onto the radians of minus rotation Y around rotation Y vector. And now I'm going to copy this because we're going to rotate it twice. I'm going to rotate it again, but now I'm going to rotate it with our XZ and along XZ vector. So now I'm going to translate our transform node, and we're going to get an original position. So 0.1p0, and we're going to translate it on original position. And now we just multiply our current position with this matrix. So transform, apply and accept. And as you can see, let's compare it. Yes, we put it exactly back. So one more thing you want to do is in our getCentroid, we have the roof ID and we want to inherit that. So we will create a new wrangle, which we will call roof ID. We will connect our getCentroid again. And it's for the primitives. And we're going to say that roof ID is the same as roof ID 0. And it's an integer. Semicolon at the end, please. Oh, I forgot the bracket. Yes. So yeah, that's pretty much it. So let's go up and see how it is for every roof. And as you can see, everything is nicely placed and we don't have this abrupt ends. So yeah, that is it for the roofs. And in the next video, we will be placing our sides. And I'll see you then. Thank you for watching. Bye bye.